This is FE Peer Review. The date is July the 20th, 2021. This video is in two parts. The first section focuses on air density in the lift equation and how that works with an airplane flying through an atmosphere in which density gradients change. The second part deals with words such as dipping the nose and pitch, and I attempt to put some definitions forward to clarify what these phrases actually mean, and then look at whether planes actually need to dip their noses, according to the definitions I provided, when flying over a curved Earth surface. I Can Science That recently released a two-part video called Dipping the Nose, which went into a lot of interesting information about the aerodynamics of how airplane flight works. It was a very nice pair of videos. It explained a lot of things. He tried to cover a lot of ground in a fairly short space, so consequently he had to keep it, I don't mean this in any way negatively, a somewhat superficial treatment. You can only go into so much detail in a few minutes, but he did a very nice job, and I'm looking forward to more of what he does. I wanted to take the opportunity to take one small issue, one small item in the list of items he covered, and look into it in a little bit more detail, because I think there may be questions in some people's minds about that. So I got the idea to do this because there was our inimitable T. Brown showed up in the comment section and got lots of reactions from everybody with his usual nonsense. Excuse me, I'm not going to be polite 100% of the time. I'm just not in the mood for that today. Anyway, T. Brown wrote, watch this video by I Can Science That. He tells you that the plane must dip the nose if Earth is curving into a sphere. He just has the belief that it magically does it on its own, and pilots don't know it. Now, that's an interesting, if you've watched the video, that's an interesting couple of sentences there, because actually I Can Science That very carefully tried to say, first of all, there's nothing magical about what's happening. It's natural. It's the result of physical forces acting on an object. It's not magical. And so, of course, T. Brown made a point of calling it magic, claiming that we're calling it magical. So there's that bit of nonsense I wanted to address. And second of all, I Can Science That was very good about saying that this phrase "dip the nose" is extremely ambiguous, means different things to different people, and that we shouldn't use it, and we should be more precise with our language. And throughout his video, he repeated that message and used more precise language. So, of course, T. Brown has to fall back on dipping the nose. I challenged T. Brown several times about what does dip the nose mean to you, which, of course, he refused to answer. He will not commit to it meaning something specific to him, because he knows very well that he can twist other people's words around if he doesn't define them. So I'm going to go into some diagrams that I've created that I hope will clarify it in the minds of anybody who's not got this grasp, what the equation of lift actually means with respect specifically to atmospheric density. That's what we're going to look at, because that has to do with dipping the nose. I'm trying to take a completely visual approach to the material here. I want it to be something that people understand intuitively. You're not going to be able to design an airplane after this. Believe me, I'm in no position to teach you how to design an airplane. I do not know how to design an airplane, but I think that I have a good intuitive understanding of the physics involved based on my own life, education, work experience, etc. And I'm hoping that by helping other people develop the intuitive understanding, it'll make it all make more sense. So what we have here is on the screen is, first of all, here's the equation of lift. Lift, L, lift is the upward force on an airplane that is countering the weight of the airplane wanting to cause, I should not use the word want, there's no volition involved here. The weight of the airplane being pulled towards Earth through gravitational attraction. That plane would just fall out of the sky if it weren't for something pulling it back up into the sky, and that something is lift. So lift, this equation here, we will never actually have to plug numbers into this equation today, but the equation is useful in explaining the factors at play. So this first factor is based on the design of the airplane, and every design of an airplane is going to have a different factor here. It's got to do with the shapes of the wings, the shape of the fuselage, and all of that. So that's a factor, and that factor is usually measured for a design in wind tunnels. It's not something you can easily just calculate. It's actually done through testing. Now that factor changes if the shape of the airplane changes. So if ailerons get moved, if the geometry of the airplane somehow changes, then that factor changes. So throughout this entire discussion, we're going to assume that none of that's happening, that there's no change to the geometry of the airplane, and this factor here is a constant which we can just simply set aside and not have to think about because it never changes throughout this discussion. V is the velocity of the airplane, the air speed. It is a speed at which the air is passing over the wing surfaces. A is the area of the surfaces causing lift. I've suggested with some arrows here that the bulk of that lift is happening at the wings. In fact, the entire airplane is probably designed, most airplanes are designed so that you are getting lift off of fuselage as well. But by far the bulk of it is happening at the wings, and so that's the area associated with the lift. And finally, the item that matters to us, rho. Rho is the density of the air. So throughout this demonstration, as we look at what I'm going to present to you, nothing in this equation changes except rho. Everything else stays constant. So what we have is an airplane in an atmosphere, and the lower part of the atmosphere, the air is denser, and it gets less and less dense as it goes up. Naturally, the atmosphere tends to be most of the time a smooth, even gradient. I have drawn it as a series of horizontal bands just so that it's a little bit easier to see on the screen, but the idea is that it's less dense the higher you go. So this airplane is flying at a certain speed, and at that particular speed and this particular shape of airplane, so we've got our velocity, our shape factor, and our area, with all of that in place, it is at a level in the atmosphere, as I show on this drawing, where the lift force, L, perfectly balances the weight of the airplane, so it does not fall to the ground and it does not rise any higher into the air. That's where the airplane stands right now. And so long as that stuff nothing changes, it continues to move forward at the same speed, in the same air density level, everything is going to stay the same. It's not going to go up, it's not going to go down, it's just going to go straight ahead. Now, the atmosphere does have variations in it. Things happen. Storms, passing from, if you're moving over hot, dry land, like the desert of Peru, and then you find yourself over the ocean. Changes like this at the ground level, storms, can cause the layers of the atmosphere, the density layers of the atmosphere, to change, to shift, to rise up, for example. So what I've shown here is our airplane. He's moving along in a straight line. Everything's fine and dandy. When all of a sudden there's a quick vertical shift and in the density layers, and the airplane suddenly finds itself in a denser layer of air. As soon as that happens, the amount of lift increases because the air density increases. If we go back and look at our equation, if rho gets bigger, lift gets bigger. Nothing else has changed. Shape factor hasn't changed, area hasn't changed, velocity hasn't changed, but rho has gotten bigger. So the lift gets bigger. Now the lift is more than the weight of the airplane. That means it's being sucked upward away from the Earth due to that higher density air, the denser air. So what's going to happen is that plane, instead of going in a straight line, is going to be sucked upward until it reaches a level in the atmosphere where the air is less dense again, like when it first started. And we see that on the left here. It is now at a higher altitude, but in an air density layer that matched the density layer it was in at the start. Let me go back and give you the big picture here. So here he was, starting on the right side of the screen, and you can see that he basically ends up at that same density layer at the end. So there was no adjustment that needed to be made by the pilot. Nothing in the shape of the airplane changed. They didn't tilt the airplane upward to cause it to lift more. They didn't fiddle with the wings to cause it to lift more. It simply went higher because the air density around it changed, which caused the lift force to increase until it again reached an equilibrium point at a higher altitude. I Can Science That had a moment in his video where he, in the beginning, where he touched on that, and that was a good way, if T. Brown had been paying attention, of understanding that there's nothing magical involved. So let's take a look. I'm not going to play the clip, but here's a clip. It looks like I'm at 450 in I Can Science That's video. He talks about what does unstable mean and what does stable mean. And in short, unstable, you can perfectly balance a ball on the tip of a pyramid, but the slightest little bit of a breeze or a slightest little bit of a bump is going to cause that ball to fall and roll off the pyramid and be gone. Whereas in this arrangement, it's called stable. You can lift and push that ball in various directions and it will tend to return to its original position. This is a factor of design. This design, somebody creating this arrangement of objects, is designing an unstable arrangement of objects. If this is somebody creating a design of objects, they've created a stable design. So this idea of unstable and stable is an aspect of design. Returning to our airplane, the airplane is effectively designed so that it will naturally return. It will naturally return due to the forces acting upon it to its original or its desired position, the position that is desired by its designer. Okay, let's look at our next scenario now. It's similar to the first one, with one small change. Instead of there being a sudden disturbance in the atmospheric layers, we have a gradual, more gentle disturbance in the atmospheric layers. Now, the plane, on a trajectory of a straight line, if it were to just continue in a straight line, would find itself in a denser layer. But what happens is that as that zone where the atmosphere is changing, as it approaches that zone, it is the forces acting on it, the lift increasing because of the density of the air increasing, it's going to cause it to drift up more gradually to its new position. Basically, it's very similar to the top example, except that it's a gradual transition instead of a sudden transition. I think that should be pretty clear. I don't need to go further with that. So we'll move on to the next scenario. So now we're looking at a situation where, similar to the previous scenario, a gradual transition in the atmosphere. But instead of the density levels going up, the density levels are going down. So the airplane, continuing in a straight line, were it to continue in a straight line, would find itself in a layer of less dense air. Now, were that to happen, same as in the previous scenario, as soon as the change in the atmosphere starts to occur, the lift force is going to get weaker because the air is less dense. And because the air is less dense, the plane the weight of the plane is going to cause the plane to start dropping in altitude. The lift force simply can't hold the plane up because there's not enough density in the air. And that situation will continue. And that plane will continue to be moving towards an equilibrium point where the lift matches the weight until such time as that atmospheric layer levels out again, and then it will be back at an equilibrium state. So where from start to finish is flying along here, the air gets less dense, so the plane starts to fall a little bit. And as it falls, it's moving into denser air. It's going down back into denser air again. And as it moves into denser air, the lift increases until, again, they're finally balanced with each other. So there's really exactly the same situation as we saw in the previous example, except the layers of air are the reverse. So here's another one. We've got density layers of air, and down here we've got a giant ball, and you guessed it, that's Earth. Let me bring this up a little bit. And the density layers of this atmosphere are wrapping around the Earth because Earth's gravity is holding the atmosphere to the Earth. So this plane, moving in a straight line, would find itself gradually moving into less and less dense layers of atmosphere, just as it did in the previous example, if it were to continue in a straight line. So as it's moving forward into less dense layers, it's getting farther. If it were to continue on that path, it would actually be getting farther from the Earth. But as it moves forward into those less dense layers, the amount of lift on the wings is decreasing, and the lift can no longer resist the weight of the airplane being pulled towards the Earth, so the plane is moving down due to its weight. The result is you get out to here, for example, and the plane has actually moved, instead of being on this line, it's now the same altitude as it was before in the same density layer, because it's in that zone where the lift and the weight are balanced. Remember, all of this is happening because we are keeping everything else constant. The shape of the airplane is not changing. The speed of the airplane is not changing. The area of the wings isn't changing. None of that's changing. The only thing that's changing is the density of the air. So for this airplane not to fall out of the sky, it has to stay in that same air density layer. And it really can't fall out of the sky so long as nothing changes, because if it's traveling at a fixed speed in consistent density layer, the weight and the lift are balanced. It's not falling. It's not going to hit the ground. It won't hit the ground until something changes. If the engine fails and it suddenly slows down, well, then it's going to start to fall. If they rev the engines up and go even faster, then it'll start to rise. But if nothing's changing, it won't fall out of the sky. It'll just keep cruising along at that same density layer, wherever that density layer goes. And it goes and it goes. So it is naturally, not magically, staying within the same density layer because it's been designed to do so, keeping the forces acting on it balanced. And as it does that, it maintains the same altitude from Earth. So, is it dipping its nose? Now, the big question, the thing that's got T. Brown all riled up, is this airplane dipping its nose? Well, what does dipping its nose actually mean? I think we need to look at that closely next. Well, according to some people, words can mean anything you want them to mean, and according to T. Brown, you don't define words because you want to be able to twist the meanings to your immediate purposes, which change from one comment to the next. So I'm going to propose some meanings for these phrases and words so that we understand what concepts we're actually talking about. That's what we'll look at next. Okay, it's time for some definitions. Now, what I'm going to describe here is how I intend to use these words. People can argue all they want about what they think is the correct definition. My point is simply to be understood what I mean. So, nose down, nose up, it says nose high, dipping the nose, level. These are the words we're going to look at. All of these pictures up here are with reference to this red arrow, which is pointing down to the ground, from the center of gravity of the airplane down to the ground, directly below it. That's a plumb line from the center of gravity of the airplane to the surface of the earth below it. Here we have nose down, which is what I am saying dipping the nose means when I use the phrase. So dipping the nose means nose down, which means that the line that we see here passing through the center of gravity of the airplane is tilted relative to the plumb line. It's tilted downward towards the front relative to the plumb line. Nose high, or you might want to say lifting the nose. That same line through the airplane passing through its center of gravity, the nose is above the horizontal, above the perpendicular to the plumb line. During normal level flight, cruising, most planes are designed to fly with their noses slightly up. This is typical. So nose high level flight. That's most of the time what airplanes are doing. And that's what I'm assuming in the diagrams we looked at before. Put your nose level and you will be very likely in a position that you intend to use to descend. And again, that's all a part of the airplane design. So nose down, that's what nose down means. It is relative to the plumb line from the airplane, center of gravity of the airplane, to the earth below, the plumb line, the perpendicular. Instead of being perpendicular to it, the nose is below the perpendicular. So let's take a look at this little diagram here. We've got this picture on the right side, which is the same as the one we were looking at before. And what I have done is I've drawn a little rectangle around each of these three positions of this airplane to examine, is it dipping its nose as it follows the curvature of the earth? Specifically, dipping its nose the way I defined it in the previous slide. What I did, I'm no master graphic designer here that knows how to use these graphic tools super well. What I did was I took this image here, put it into Photoshop, I snipped out these rectangles, and then I copied and pasted them back in here onto my slide. So we've got A, B, and C. And I didn't do a 100% perfect job. Like I said, I'm not a whiz-bang graphic designer. So I didn't get this perfectly aligned and all that. I'm not going to fuss about it. If you want to fuss about it, you can. You show me how to do it better if you're going to make a fuss about it. Yes, I'm talking to you, T. Brown. You do it better than this, and I'll pay attention. You do nothing except word salad, and I won't be bothered. Okay, A, B, C. A, B, C. The plane is in position A. It is flying with its nose very slightly up in level flight as per the upper left diagram here. It has now moved on to position B. It is still flying perpendicular. Here's the plumb line from the center of gravity of the airplane down to the ground, and it's still flying slightly nose up. Nothing has changed. Position C. There's the plumb line. There's the center of gravity of the airplane, and it's still flying slightly nose up. It has not changed altitude. Its nose position has not changed as it moved from A to B to C. At no time did its pitch change. There was no need for its pitch to change. Its pitch, keep in mind, is moment by moment with reference to its plumb line. And its plumb line is pointing towards the center of the earth. So no, it does not go nose down It does not dip its nose according to the definition I gave. And if you want to use a different definition, that's fine, but I'm the one doing the talking. According to the definition I used, it is not dipping its nose as it follows the curvature of the Earth. It doesn't need to. It simply stays with its same relationship to the ground below it as it moves over the curved surface. It does not rotate relative to the Earth. Now we go out into space like we are looking at this diagram here, and we are far off the planet. And we're thousands and thousands of miles away looking back at Earth, and there's a plane over the North Pole, and it's gradually heading due south down to the equator. From our position off of the planet, we see this plane flying in a curve. You want to call that nose down? You can call that nose down. When it gets down to here, it's going to be flying upside down. You figure that one out. But from its position relative to the Earth's surface, which is where we are right now, at least that's where I am, and I expect most of my audience, from its position relative to the surface of the Earth below it, it never changes its pitch. Now, if you're going to debate that, I think it would be really great to show me some pictures, some diagrams. Who was it? Was it Napoleon who said a picture is worth 1,000 words? I've already probably spoken a couple of thousand words and shown you just a few pictures. You show me some nice pictures that prove that I've got this all screwed up and backwards and wrong. Otherwise, no, planes do not need to, quote, dip their noses, if by that you mean pitch down. Okay, enough of this. I've beat this dead horse as much as one can beat a dead horse. So I will leave the rest of it to those of you who join on in the comments. And I wish you all a great day. Remember, do all those nice things like liking the video and subscribing and sharing it and all of that. Bye-bye.